Today, we are giving AI a physical interface by talking and focusing about embodied AI. Why don't you quickly introduce yourself? And I would be very curious to hear a bit more about your background and maybe also very shortly what you're currently working on. You want to start?
Sure. Hi everyone, I'm Zihan. I have a technical background. Did my PhD in Imperial more than 10 years ago, and then when I finished there, I decided I wanted to try the world of entrepreneurship. So I went through an accelerator called Entrepreneur First, and started a company called Magic Pony, which worked on video compression, and we were, I guess we had good timing in that we started just when deep learning was just starting to take off. So we were probably one of the first teams and companies to leverage deep learning to do visual processing, and less than a year after we started, we exited to Twitter, and I joined Twitter in 2016, and I stayed on for 5 years and became head of applied research there, and did a lot of work in combining, looking at how we bridge the academic research world and connecting to the product world, and particularly leveraging new machine learning techniques in product settings. And then I took a 3-year break before I decided I wanted to get into robotics. So as of about 6 months ago, I co-founded a startup called Patented Robotics.
Thank you. Joining me first. Mohan?
Amazing. First of all, thank you for having me here. Pleasure to meet all of you. So my degree, I'll start like Zehan did, was 800 years ago. I did a PhD in physics. And then in '99, I started working in an embodied AI company before the term embodied AI was cool. So we did autonomous robotic systems for the chip makers deep in their factories that did computer vision and machine learning to detect problems. And anecdotally, when I joined them, the design rules were 250 nanometers. That means the critical dimension between two structures on the chips were 250 nanometers. And when I left them 18 years later, it was 7 nanometers. So I saw that Moore's law really scale every 18 months, 24 months, new products, more capability, leveling of the design rules. Very exciting. I don't think I see that level of tech anywhere. And then I did some single-arm robotic applications for the fulfillment centers at Amazon. And 6 years ago, Hussein, one of the co-founders of Fido, reached out and got me from Seattle to London. Then I came to London and spent the last 6 years in a couple of startups here. One was on Fido for three plus years, and then Tractable, one of the other computer vision companies here in the city. And now, since January, just co-founded a robotics and healthcare company to do autonomous diagnostics and non-invasive interventions. It's a pleasure to be here.
Pleasure to have you. I feel like when we talk about embodied AI, of course, autonomous driving has been around for decades, and we also talk a lot about humanoid robots. I want to start by setting the scene a bit, by asking you, what do you believe will be the first frontier of really accessible embodied AI systems, and why? And accessible in terms of it being scalable, but also from a performance level really be at the level where they should be.
Okay, sure. So I think this is already in motion. It's in the warehouses. So robotics in warehouses has been around for a long time. It's a controlled environment, it's structured. You don't need to have a lot of capability in the robots. You can structure the environment so the robots can still do a lot of work very fast, very reliably, and you can do simulations quite well because of a constrained structured environment. You can increase the level of automation in a very controlled manner. So this has been on for a while. Amazon robotic warehouses, they built so many different robotic applications inside them. So I see that as sort of the first, most useful, and the best part is there's a good direct commercial return on investment on that, so you can see that right away. So yeah, let's talk about that.
Yeah, so I think it depends a little bit on what we define as being embodied AI. I think you can also argue, your smartphone could be considered, embodied AI. You've given a physical presence to basically having some AI models that could be running live on your phone, that can sense and interact with the environment or understand the environment around you. I think it's sort of so it depends a little bit on sort of our definitions, but in my view, I think a lot of this really comes down to what is the primary data source for that AI and how does it process that? Does it have a physical body that it does it in, and does that matter to sort of what it is doing within that environment that it's working in? I think a phone kind of still ticks the right boxes because ultimately at the end of the day a phone can run out of battery, so you have to worry about sort of like, okay, yes, it lives inside this device that you can move around and it's mobile and it has to be able to sort of it's useful within sort of our environment in that way. And maybe it's sort of like playing around with the definition a bit loosely. The other thing is also looking at, say, robot vacuum cleaners. So if you already have one of these in your home, you can argue that is actually one of the first steps of embodied AI, particularly in terms of how it's entering the consumer space and their homes. And I think actually for Roomba, they originally wanted to sort of position themselves as an embodied AI and more general purpose robotics, but it focused down towards solving just vacuum cleaning and became a more specialist robotics company as a result. But yeah.
Would you agree there, or what would be your one sentence definition of embodied AI?
Yeah, so I agree with the definition there because as I see it inside the smartphone, you have sensors, you have intelligence talking and triggering things, autofocus mechanisms or whatever. So from that point, it would still be an embodied AI system. It's just not explicitly moving something around in the real world. So in that sense, I do agree with him. But in general, what I find is we look for bigger motions, we look for bigger things, bigger movements and actions of robots in the world.
Talking about bigger movements, certainly there, I think a term of humanoid robots, I think is probably a pretty close one. When we had a chat in the kitchen before, you talked a lot about the form factor when it comes to, of course, embodied AI in general, but I think if you take the humanoid robots as an example, this is an important question. So if you were to design now a humanoid robot, how would you proceed giving a form factor criteria?
It's a great question. So I was in a robotics conference a few years ago, and I saw one of those robots called Sophie. Has anyone seen Sophie? Right? And if you actually interacted with Sophie, my hair was standing because I was starting to perceive Sophie as a real person. I just couldn't. I just had to step away, walk away. This is just me personally, right? I couldn't stand there and interact with Sophie. So to me, it always bothers me that we maybe are jumping too far ahead with the humanoid form factor. It has a lot of social implications that we're not thinking through at all. And I worry that for a lot of the robotic automation that we're looking to develop and deliver to the world, we don't need the humanoid form factor. Washing machines and dishwashers work just as well. Okay, you don't need a human standing on top of your sink washing your dishes. So I don't know that we need the humanoid form factor, and I worry that I can understand the commercial allure for someone like Musk to build a humanoid, the ChatGPT equivalent of a robot, but it scares me. I think I worry a lot.
Yeah, I so agree that I don't necessarily think that the humanoid form factor is basically what we should be aiming for. I think it is a valid form factor because I think that's what we are, and we have built an environment around us. But who's to say that it couldn't be something else completely? Like, yes, maybe it should be the same sort of, take up the same amount of space as we do as humans. And if we want to have something that can be general purpose, it most likely will have some limbs and arms and so on, but could have multiple arms. It doesn't need to be on legs. It could be on wheels. It could also have completely different sort of body. It could be sort of completely soft shell as opposed to sort of hard form factors as well. So I think there's actually a lot here that we kind of haven't really explored, and we've kind of let basically sci-fi dictate that we should go in this direction because it looks cool. But actually, I think when we think about sort of the use cases, the practicalities, and also like just, how much does it cost? Like, these are all the factors that will come into play as to actually, does this make sense? And I think where we are today is that we're actually a little bit premature as to really understanding the right use cases, both from a commercial perspective, but as you rightly said, from a wider societal implication perspective. Like, we don't really know what that societal implication is going to be like. If we just end up with like as many human and robots as humans, what does that mean for society, right?
Embodied AI is super hard. I think probably everybody in the room would agree to that. If we talk a bit about the technical limitations and also the challenges, and maybe moving away from autonomous driving and also humanoid robots, also maybe in areas that are closer to where you're currently active, what would be like one technical limitation that would like really change the game if we could solve that with a finger clip?
You want me to start? Okay. I think there's something still yet to be done on sort of low-level integration between different components, different suppliers, etc. We haven't come up with like a standard for how do we build, a embodied AI as a hardware form factor in terms of its components. I think if we got to the stage like we do with like the PC industry, where we have very standard like here's your main board, here's your CPUs, RAM, etc., and you just literally can take suppliers and components from different countries and put it in, just works. That would be a game changer for robotics.
Yeah. So I'd like to just zoom out a little bit. So if you look at what makes the problem of embodied AI hard independently, and then I'll come to specifics of my problem. So we get data from sensors, right? And sensors are inherently noisy. They generally can't see the entire environment, perceive the entire environment necessarily in a complete fashion, and they have their own noise. So that's one aspect that makes it hard. The other aspect that makes it hard is when you want a robot or a mechanical device to do a certain set of actions, it's hard. As humans, we do certain things so naturally, to define that and then to get them to do that is very hard. And what's hard there is the edge cases, the long tail of edge cases. Someone experienced as we've grown up from our childhood, what we're really learning are how to deal with all the edge cases that happen. When you see a step, you go down. In fact, here's an example. When you've got a child, let's say, who's trying to carry something heavy in your house, you check, are you okay? Are you okay? And the child is able to say, yes. Sometimes they're wrong, but most times they're right. They actually know what they're doing, right? And so we don't have this kind of a training vehicle to convey. The best thing we have is imitation learning from demonstrations, blah, blah, blah. But these are more sort of the bulk distribution, not all the edge cases. So this is at the very high level, right? So this is what makes embodied AI really hard. The noise of the sensors and the inability to articulate and define these motions and teach these. We have no fundamental basis to break any motion into a set of primitives and then just reconstruct any motion from those primitives, right? So those are the two things I see at a high level. Specifically for any given application like ours, so by the way, what do we do? Right? I didn't tell you what we do. So what we do is we want to offer the clinicians, the doctors that you see, the right data on demand, so high precision data on demand. And what we're looking at, the particular modalities are the analog, quote-unquote analog modalities, which means where the human ability of the doctor is necessary to see, right? Whether it be looking at your pupil dilation, whether it be looking at the palpitation, whether it be auscultation, listening to your chest or whatever, they're doing this in an analog fashion, and there's no need for that. So what it does is, it limits how many people the doctor can see, because they have to do this one by one by one. And so what we want to do is we want to bring autonomy to it to really make that digital and make that data available on demand at high precision to the clinicians, human clinicians today and AI clinicians tomorrow. So That's really what we do. So in this case, we have a different set of problems because we are now, embodied AI comes in a variety of taxonomies, so to speak. One is it's workers in the factory, it's workers stacking shelves or whatever. Then there is the autonomous car or the AI that is working with you, that's touching you, but it's a collaborative mode. So if it touches you or gets close to you, it stops working and pauses and so on. But in our case, it's actually different because when you're palpitating, you're just hitting a body doesn't mean you can stop. You have to actually go in. You have to engage with how the body's elasticity and the muscles and the bones go without injuring. You have to get there. So we have a different set of problems that I see are quite challenging. There are no sensors to know. The force sensing also sort of breaks, when it comes to these kinds of soft issues and understand that. So we have a set of problems that are quite a bit different from your typical embodied AI system.
Can you maybe talk, or do you want to talk a bit about how this technically can be solved, or?
Okay. So there are two issues here. One is how can you ensure safety, right? When you're pushing on the body, how do you make sure that you're safe? And for safety, what we are doing is we are looking at a hierarchical safety system that has parallel stops. So a 6th level hierarchical safety system that has enough stops in there that will ensure that anyone, if triggers, it will stop the robot and come back to it. Now we have so that's one way in which we look at it. The other way is you still need to push in, and so you need to know how much force to apply, how far to push in with signals, and this will be dependent on data acquisition. So how we get data through a teleoperation system to understand the statistical process control bands around that, and then build the AI around those SPC bands. So that's how we are going about it. May not be the best way, but it's how we are going about it.
I found also your point very interesting on the integration one, and it actually surprised me a lot, just because if you look at the daily news, every day there's a new infrastructure company, of course not with regards to embodied AI, but open source frameworks, everything around agents. Why is this falling short, and what would be your expectation there? Or do you think it is also just because it's hard, or can you elaborate a bit on that?
Yeah, I think it ultimately comes down to the use cases that you're sort of imagining, and whether you can use something off the shelf that's really pre-made. So at this point, there are a number of suppliers basically just supply arms that you can already experiment with. But there are limiting factors to the arms they provide, and particularly like how much force they can provide, what's the degree of freedom in terms of maneuverability and so on. And for certain applications, you basically have to rethink this and go, okay, we're going to have to start from basically the low-level hardware form factor to reconsider what's the right sort of approach. And that's basically where then you encounter the fact that, okay, all these suppliers have their own firmware. They have, if you order parts from China, the firmware will have instructions in Chinese. So if you don't know Chinese, that obviously creates another barrier for you. And then basically there is no standardization because there isn't any incentive right now. So I think it really comes down to, again, like, can you leverage something already pre-made that then you're looking to deploy? So maybe this is one of the attractions for going straight to human form. Someone else is manufacturing and it can already do a whole bunch of things. But ultimately, then the question comes down to, does that form factor become cost effective enough for the application you're doing? Because if it's more generalizable, it generally is not going to be as cost effective as something more specialized. So there's always trade-offs in that.
Can I add something? I think absolutely. So what you're saying is to build a first system, right, and design the system and build that product and ship it out. There's another part which we're not thinking of today at all. And when I talk to robotic suppliers, they stare at me. It's the forklift upgrade problem. So one of the motors in one of the joints is going to fail. What do you do then? Oh, we'll send you a new robot. Oh, really? Who's going to take the cost of that new robot now? And how much matching do you have between these things? So you can go buy from reputed companies, right? A 22,000 pound robot from Franca, or you can buy a 30,000 pound robot from Kinova, or whatever. Really great robots. You can build your product, looks great, put it out in the field. 12 months later, it breaks. Who's going to take that 32,000 pound bomb now? You know. So these are not designed for repair in the field. They're just not designed for that. And so I think apart from the supply chain problem, we have a design problem in the arms today that is not thinking of wide scale deployment.
I would like to talk a bit about training approaches, but just before, another question, because I think when listening to all of the challenges that you brought up, I think I'm asking myself, and I think you're currently in that situation, that your robotics companies or embodied AI companies are still relatively young. And I think you see a lot of embodied AI companies coming out of research where a team has been working on it for years, and then it's ready to be commercialized. So for somebody that maybe has not done research within a university environment for 5 years, how do I start? How do I get an embodied AI company off the ground? What is the first 3 things to do apart from the whole legal things? We don't have to talk about that.
I think maybe the starting point is actually understanding what's the problem space that you're looking to address. And I think one of the things I've sort of seen from some of the hype that we've seen around embodied AI, and particularly humanoid robots, is a lot of the times we haven't fully identified actually what is this robot going to be doing, what's the use case of fulfilling, and how does that deliver the cost benefit that people are expecting. So I think just working from first principles as to, okay, what's a problem I need to solve? Do I focus on a particular part of that embodied system, or do I want to look at the application use case? That's probably the first deciding factor, because there's problems along all of this, and embodied AI is basically looking at how do you combine hardware and software in a way that's somewhat seamless towards some end goal in terms of the physical application that we want. And each of these has different problems that could be addressed.
Can I add something?
Yeah, please.
So I think I totally agree with that. That's the product level question, which is really what can the technology deliver and what is useful and commercially, what can you actually build and sell in any realistic time frame, right? But then there's another aspect, which is the building of it. So today, if you look at a lot of the university research groups, there's just a bunch of demos, right? They're great for papers. You write your paper, go to IROS, and it looks great. You get a lot of, you show something here, something there on a phantom, on a simulation. But the real world is very different. Just so different that even if you hire these 5-year veterans, 8-year veterans from the research world, you don't have a team. So I would say you need an industry veteran who really knows where these edge cases are. How do you design the system for these edge cases? How do you have a correctable system where you can actually, let me take an example if you don't mind. Do we have time for a minute?
Yes.
Okay, so if you take the autonomous vehicle space, right? So if you take 2 approaches, which is Wave and Tesla to some extent take the end-to-end learning approach. So you go pixels, outcome, controls, what do we do? I brake, do I turn, do I accelerate? And then if you look at Waymo, they've taken a more hybrid sort of modular approach where they put all the sensors they need and they have the modularity and then a bunch of narrow AI modules that come into the system and then the system gets built. Now that is, so both of them have advantages, but the work is still the same and people don't recognize that. The work in the first system is how do you break the system, how do you build each of these modules, how do you integrate the system, how do you, the advantage is it's correctable now and you need lesser data because each of the systems is simpler and you use inductive biases to build the relationship between the narrow AI systems. But on the other side, the end-to-end learning approaches, it looks easier, you get data, but now all of a sudden when failure modes occur, you have to work extremely hard to build simulation cases. So the effort you spent in modular cases here, you're going to spend in building amazing simulations so you can generate the data so that you can then train the end-to-end models. So there's no shortcut, even though it looks like one is shorter than the other.